Okay, everybody, we're going to go back to the start of this PowerPoint and we're going to talk about how we got these numbers. Now, I have done this several times a day. I am learning how to use a new screen capture program, and it has been a work in progress. But remember, we went through number sense, 110 times 200. Remember that you can just kind of underline your zeros or keep them in your brain. You're going to add 3 zeros at the end of your work, but you're multiplying 11 times 2, which is 22, and then you're adding the 3 zeros to make it 22,000. All right, so here, one of you popped up with 45, and that's correct because 15 plus 45 is 60. Now, this one gave y'all some trouble, and I want to just make sure that you remember to always look at where you're starting on your measure. The measure starts at 3, so that's 1, 2, 3 inches. And then this little bit right here, we needed to go backwards and see how much that is of the whole. So there's 1, 2, 3, 4, 5, 6, 7, 8 in a whole. So that little bit was 1/8, and that's where we got 3 1/8 as our answer. At a rate of 40 words per minute, how many words can Valerie type in 20 minutes? So 40 words per minute and 20 minutes. The minutes will cancel. Your units can help you figure out if you're doing it correctly. And we are left with words, which are right there. And 40 times 20 is 800. So 800 words is what Valerie will type. So when we're doing our scientific notation, we're going to start here at the end and go 1, 2, 3, 4, 5, 6, 7, 8 till we get right after the first digit. So 8 is the number of spaces. We're going here to 0.8, but we know our number is really much larger than that, so we're multiplying by 10 to the 8th, and that is our scientific notation for that one. Geometry. Now, we went over this one in class, but I wanted to show it to you again. When we're dealing with this situation where we have two sides, and we're trying to say, what could the third side be? Well, if we laid this triangle down flat, like we took this height of the triangle and we made it very, very, very short, okay? The shorter we went, the longer this side could be. And at your very, very, very smallest little height of your triangle, then this 22 and 10 would be almost the length of the other side. So the other side would be a little bit less than 22 plus 10, which is 32. So to find the longest that this third side could be, we add the two other sides together, like we're just laying this whole triangle flat like a cardboard box. We would flatten it down, and that third side would be less than 22 plus 10, because if it was equal to 22 plus 10, we would not have a triangle anymore. It would be a flat line. But to find the smallest, we're actually going to think about, what if the 22 was going up, but then there was such a small angle right here that the 10 was coming back here. And then that third side would just be joining the two together. So 22 take away 10 would be the very smallest, or 12. So this third side x must be between the difference of the other two sides and the sum of the other two sides. So then I worked another example. If we had 5 plus 5, 8 in x, then this x would have to be between 13, which is the sum of 5 and 8, or 3, which is the difference of 8 and 5. So x is between 13 and 3. Those are fun. Okay, so powers and roots. I realized that in class I did not read this correctly. List the perfect squares from 49 to 100. Since it said from 49 to 100, 49 and 100 should have been included. I did not do that in class. I treated it like a between, but it's not a between. It is a from. So we should have included that. This is 7 squared, 8 squared, 9 squared, 10 squared, and that would be our answer. Okay, this one was fun. 25 times 4 is 100, divided by 2 is 50, minus 1 is 49, square root that is 7. 7 times 7 is 49, plus 1 is 50, times 2 is 100, minus 1 is 99, divided by 11 is 9, square root that is 3, times 7 is 21. Okay, so here we are with the next little bit. Probability is the likelihood that a particular event will occur. To represent the probability of event A, we use the notation probability of A. And we express probability as a number ranging from 0 to 1. So remember, 1 is the same as 100%. And so when we're talking about probability, a lot of times you'll hear 100%, which is the same as 100 over 100, which is 1. And if it's got a probability of 1, it is absolutely certain. If it's got a probability of 0, it's unlikely. If it has a probability of 1/2, that's the same as 50%, which means it is 50-50. It is neither unlikely or likely. It's right in between. Okay, so sometimes in Saxon, they'll use as likely as not, which means, hey, it's 50-50. It could go either way. Probability is a ratio of favorable outcomes to possible outcomes, or the number of favorable outcomes over the number of possible outcomes, or the total number of outcomes. So here we're going to practice this a little bit. The spinner shown at right is spun once. What is the probability the spinner will stop? In sector A. Okay, so there's 1 A out of 4 possible. So 1/4 is the probability. In A or B, so now our favorable is A or B, and there are 2 favorable outcomes out of 4, and we know that 2 out of 4 can be simplified to 1/2. Okay, and then on the last one, it said sector A, B, C, or D, and that means all of them. So the probability would be 1. 4 out of 4 is 1. The face of the spinner is divided into fourths. There are 4 equally likely outcomes. One outcome, A, is favorable. So we got probability of A is 1/4. That's what we found right here. Okay, probability of A is 1/4. Probability of A or B, remember we said was 1/2, but here they're doing it a little bit more mathematically. Probability of A or B is the probability that A happens plus the probability that B happens, which is 1/4 plus 1/4, which adds to 1/2. And then the probability of A, B, or C is 1 because every spin results in one of those. Okay, so now we're talking about probability may be expressed as a fraction, as a decimal, or as a percent. We often use the word chance when expressing probability in percent form. In example 1, probability A is 0.25, which means that the spinner has a 25% chance. Now remember, probability of A was 1/4. And that's where they're getting the 0.25, because we know that 0.25 is the decimal of 1/4, and 25% is the percent that goes with 1/4. So here we're talking about odds, and odds are different from probability. Odds is the ratio of the number of favorable to unfavorable outcomes, and is often expressed with a colon. So here's a colon, and odds means we're going to have favorable to unfavorable. This is hard to write on, guys. Sorry about favorable. Okay, is 1 to 3. Because looking back at this, we had 1 favorable and 3 not favorable. So that's 1 to 3. The probability is 1 to 4, but the odds are 1 to 3. They're not the same thing. Probability is favorable to total. Odds is favorable to unfavorable. If the spinner in example 1 is spun once, what are the odds the spinner will stop in sector A? Okay, so here we're talking about example 1, and it says A, so it's going to be 1, 2, 3, and we usually will put that with a little colon. The odds are 1 to 3, which they show right there. All right, so now we're talking about sample space. And sample space of an experiment is the collection of all possible outcomes that are in the experiment. We can record the sample space in a variety of ways, including a list. Here would be a list or a table. We can, and then, for example, if a coin is tossed twice, there are 4 possible outcomes. So here I made a tree diagram. In a tree diagram, we just start at the beginning and we toss 1 coin. And that first coin, that first event could be head or tail. But then from there, we move into the second toss, which could be head or tail. And then the second toss for the coin that was originally a tail would be head and tail. So this covers every eventuality. And notice that we have 4 outcomes. We have head, head, which is right here. We have coming up here head, tail, which is head, tail right there. And then we come down the tail trail here. Tail, head, tail, tail. Tail, head, tail, tail. Now, the cool thing about this is once you learn how to do, we call these truth tables here. And these little truth tables can be very helpful in figuring out our sample space. So notice that what I did, if I were going to make a little diagram, I would say, okay, half of these are going to be heads, and then half are going to be tails, and then I'm going to make head, tail, head, tail. And that gives me every eventuality. And if you look back, then both of these had a head to start off with, and both of these had a tail to start off with. Okay? So we'll work on those some more. So in the list and the table at the right, we use heads for heads, H for heads, and T for tails. And the sample space was head, 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 tail, tail, head, and tail, tail, which is exactly what I got right there. Okay, knowing the sample space for an experiment helps us to calculate probabilities. Referring to the sample space above, can you find the probability for getting heads at least once in 2 tosses of a coin? So remember, this sample space is 2 tosses of a coin. So here has a head at least once, here has a head at least once, here has a head at least once. So the probability of having a head at least once is 3/4. Okay, now what if they had said, what are the odds of having a head at least once? We would say 3 to 1, because we would be saying, what are the odds of at least a head to not at least 1 head? Okay, so there's only one that has not at least. This would be odds. And this one in front would be probability. 2 different things. You've got to know those. Okay? Now, if Javier spins the spinner in example 1 twice, what is the sample space for the experiment? Okay, now going back to example 1, we have this. Okay? So we have A, B, C, D. So let's go over here and go. Oops, let's go to Javier here. So we're remembering here that we have A, B, C, and D. Okay, now given that little picture, if we were going to do a sample space, we would say, all right, let's do A, and we're going to have each one start with A. because we've got 4 things going on here. So A, we could spin an A on the spinner spinning twice. We could have A, B, A, C, A, D. Okay, oops. We could have had an AA, couldn't we? I need to move those down one. We could have had an AA, an AB, an AC, and an AD. Okay, now those are all the possibilities with an A on the first spin. So then we say, well, what if the first spin was a B? Okay, so then if the first spin was a B, then we could have had an A, and a B, and a C, and a D. Well, what if the first spin was a C? Then if the first spin was a C, we could have had an A, and a B, and a C, and a D. And then lastly, we have to consider, what if the first spin was a D? Okay, the first spin was a D, then we could have had for the second spin an A, and a B, and a C, and a D. All right, now, that's not the only way to figure out that sample space, but that is a very good, consistent way. Now, notice, we had 4 choices for the first spin and 4 choices for the second spin. So the number of possibilities that we have in our sample space is 4 times 4, or 16 possible outcomes. So this would be the sample space, AA, AB, AC, AD, BA, BB. Okay, so all of these are in the sample space. 16 items are in the sample space. Okay, so here they didn't go into it, but they will go into it later on, more in the before we get to the homework. Okay, the complement of an event is the set of outcomes in the sample space that are not included in the event. The complement of getting heads at least once in 2 tosses is not getting heads at least once. The probability of an event and the probability of its complement total 1, because it is certain that an event either will occur or it will not. If we know the probability of an event, we can find the probability of its complement by subtracting the probability from 1. Okay, so here, the spinner in example 1 is spun twice. Okay, so example 1, we've got our A, B, C, D, right? Okay, and then it says, is the probability of spinning A more likely with 1 spin or with 2 spins? Okay, so let's figure it out. It makes sense to me that you're going to be more likely to get an A if you have 2 tries, right? But let's look at it with our probability. If we have 1 spin, we spin once and we've got 1 out of 4 chances. So 1 spin, we have a 1/4 chance of getting an A, okay? But if we spin twice, we have to go back here. How many A's did we have in here? We had an A in there, 2, 3, 4, 5, 6, 7. We had 7 possible events in our sample space that would allow us to have an A. So 7 divided by 16. Okay, so we're going to go back here and we're going to say if we had two spins, then 7 out of 16 would be the probability of getting at least 1 A. So now, which is more, 1/4 or 7/16? 1/4 is the same as 4/16 when I multiply the numerator and the denominator by 4. And 4/16 is less than 7/16. So the more I throw a coin, or in this case, spin a spinner, the more likely I'm going to get what I want. Okay, so as we expected, you're going to have more likely if you throw it 2 spins, a roll or spin 2 spins. Find the probability of getting A at least once. Okay, so if we're finding the probability of A at least once, we're doing that right there. Okay, and find the probability of not getting an A at least once. So here we go back here. If we were going to get an A at least once on 7 of them, then wouldn't the complement, be not getting an A, and we would not get an A on 9 of them, wouldn't we? And so that would be 9/16 that would not give us an A. All right, so here we go back here. The complement is 9/16. And remember that the probability and the complement of that probability always add to 1. And when we add 7/16 and 9/16, we get 1 because 16/16 equals 1. Okay, so the spinner in example 1 is spun twice. Predict, is the probability of spinning A more likely with 1 spin or 2 spins? Okay, well, we just showed that, okay, but I don't think they're really going to show that. We did show it with the 1/4 and the 7/16. Find the probability of getting A at least once, okay, which was 1/4. I think they may be going into what we just finished doing. Find the probability of A. We determine the sample space, which we did, and they did it the same way we did it. C, AA, AB, AC, AD. And, oh yes, they are going to do it. Okay, so here's the 7/16 that we just found, and 7/16 is greater than 1/4, so that's the A. And then find the probability of not getting A at least once was 9/16, remember? Okay, and here they're going back to 1 minus the 7/16 gives you the 9/16. And I showed you the 9/16, right? 1, 2, 3, 4, 5, 6, 7, 8, 9/16. So we have done that thoroughly, okay? But 1 minus the probability gives you the complement, and 1 minus the complement gives you the probability. They go hand in hand. All right, so now we're on example 4. Okay, so we are on this next one here. Nathan flips a coin 3 times. Predict which is more likely, that he gets heads at least once or that he will not get heads at least once. Okay, so let's think about it. 3 times of a coin flip. The first thing that I'm going to do just for your instruction is start with a tree diagram. This makes it very easy to see. So we've got tails, heads. We could start with heads. It really doesn't matter. And then we're going to have tails, heads. And then from each one of those, we're going to go tails, heads. Okay, and then we're going to go tails. The big thing is be consistent, whether you put heads first or tails first. It really doesn't matter. I usually put heads first, but I didn't this time. All right, so we're going to do the same thing here. We're going to go tails, heads. And then from each one of those, we're going to go tails, heads. Ran out of room here a little bit. And from each one of these, we're going to go tails, heads. Okay, so now we're going to, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 in our sample space. Now let's see if we can wrap our head around it. Remember, when we had 4, we ended up having 4 squared, or 16. Now we have 2 outcomes. We have a head or a tail. Now we have 2 outcomes, but we are flipping 3 times. So the number of outcomes in our sample space is 2 to the third, or 8. Okay, so here we end up with tail, 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 and then tail, tail, head, tail, tail, head, and then tail, head, tail, and then tail, head, head. Now I want you to understand this. We don't have room to do all of the heads down here, but I want you to see this. I took half of my sample space. So I'm going to 8 in my sample space. So I made 4 of them tails. And then I made 2 tails and then 2 heads. And lastly, I made tail, head, tail, head. And I would alternate. So if I were going to do this, we're just going to get another slide here to work with, just so we have a nice clean slide. So now I'm going to do this problem, not with a tree diagram, but with a truth table here. So I'm going to start, and I'm going to start at the top. Tail, tail, tail. Since I know there's 8 outcomes, I'm going to make 4 tails. And then right below, I'm going to make head, 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 head. Okay, I guess I could get rid of that. No, I can't, not right now. All right, so then for the second one, since there were 4 to start with, now I'm going to have 2 tails, and then followed by 2 heads, and then followed by 2 tails, and then followed by 2 heads. And lastly, the last one I'm going to alternate every time. Tail, head, tail, head, tail, head, tail, head. And that way I get every single possibility. And there are the 8 in the sample space. Okay, so now let's go back and look at our question. Which is more likely, that he will get heads at least once, or that he will not get heads at least once? So let's go back and look. Heads at least once occurs here, 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 and here. Heads at least once was 7 out of 8. Now realize that heads not once means that there's tail, tail, tail. And there's only one chance that you're going to get no heads, and that's tail, tail, tail. So no heads means 1/8. You have a lot more probability to get 1 head than you do to get no head. All right. So then it says find the probability of getting heads at least once, which we did find was 7/8. Find the probability of not getting heads at least once, which we found out was 1/8. Okay, so now we'll skip our little extra slide. And here they go into it. Okay, the probability of getting heads in one toss is 1/2. Since the opportunity to get heads at least once increases with more tosses, we predict that getting heads at least once is more likely than not getting heads. Okay, so here they're doing a tree diagram, which we did something similar, right? Theirs is a little neater than mine, but 7 out of the 8 outcomes have at least 1 head. So we got that result, didn't we? Okay, then it says the probability of not getting heads is 1/8 because there's only one option, theirs is at the bottom, that has no heads at all. Okay, and remember that 7/8 was the probability of getting at least 1 head, and 1 minus 7/8 is 1/8. And how do we do that? We remember that 1 is 8/8, and 8/8 minus 7/8 is 1/8. Okay, so we distinguish between the theoretical probability, which is found by analyzing a situation, and the experimental probability. Now we're going into two more definitions, which is determined statistically. Experimental probability is the ratio of the number of times an event occurs to the number of trials. For example, if a basketball player makes 80 free throws in 100 attempts, then the experimental probability of the player making a free throw is 80 over 100, or 4/5. The player might be described as 80% free throw shooter. Okay, so here, if you're talking about experimental, that means what actually happens in the number of trials. Okay, so in baseball and softball, a player's batting average is the experimental probability expressed as a decimal if the player getting a hit. Okay, so Emily is a softball player who has 21 hits at 60 at bats. So that's her history. It gets 21 out of 60 at bats. So if you were going to take her theoretical probability, you would say that is what she has done in the past. That's her experimental probability. It's what she has done in the past, not theoretical. Express the probability that Emily will get a hit in her next at bat as a decimal number with 3 decimal places. Okay, so this is the probability that she will get a hit at her next at bat. So if we were going to turn this one into a decimal place, we would do a little bit of math here. Okay, so 21 by 60, we're going to put a decimal right here, and we're going to put a 0, and 6 goes into 21 3 times. I'm going to put my decimal right above. 3 times 60 is 180. Okay, and then I subtract, and I get 30. And I bring down another 0, and then I've got 60 into 30 is 5. Okay, but they said 3 decimal places. So we would say her batting average is 350. Okay, and then it says use a substitute hitter whose batting average is 300, okay, or 0.300 thousandths. Batting averages are usually expressed without a 0 in the ones place. How would you advise the coach? Emily's at bat is better than the substitute's at bat, isn't it? She's got a better chance of getting that next shot. So there's a little bit of probability even in playing baseball, right? Okay, so here they did the division just like we did. They said her batting average is 0.350 and the others was 300. So it would be advisable for the coach to let Emily bat. Okay, so here we're in our practice set, and we're going to... So we are at the very end, and we're going to do our practice set and our written set. So here we go. A number cube is rolled once. What is the probability of rolling an even number? Express the probability as a fraction in a decimal. So remember that a number cube is just a die. Okay, and so a die has 1 on one side, and then a 2. Remember what a dice looks like, and then a 3. Okay, and then a 4, and then a 5, and then a 6. So these are the numbers on a dice. Okay, so a number cube is rolled once. What is the probability of rolling an even number? Well, this is an even number. This is an even number, and this is a even number. And there are 6 sides altogether. So 3/6 is 1/2. Okay, so expressing that as a fraction and then as a decimal would be 0.5. So 0.5 or 1/2 would be the answer. B, a number cube is rolled once. What are the odds of rolling a 6? Well, if you have a number cube, there's only one 6. 6 is one of the sides, right? So we're going to say 1/6 out of 6 different sides. 1, 2, 3, 4, 5, 6 are the options. So 1/6 is the probability. But remember, probability is not the same as odds. Okay, so probability is 1 to total. Odds would be 1 to 5. Okay, here's the number of 6s that there are, and here are the number of not 6s that there are. So 1 to 5 would be the odds. You have to be very careful when they say that odd word. Okay, now C. If the chance of rain tomorrow is 20%, then it is more likely to rain or not. Then is it more likely to rain or not? So the chance of rain is 20%. Okay, now 20% is less than 50%. Okay, 100% would mean it's surely going to rain. So you're going to say it is unlikely to rain because this is less than the 50% mark. So we're going to say it is unlikely to rain. It says, then is it more likely to rain or not rain? We could say it's not likely to rain. Okay, so unlikely, not likely, whatever you want to say. Okay, and then what is the chance it will not rain tomorrow? There's an 80% chance that it will not rain tomorrow, right? Okay, so D, a coin is flipped 3 times. What is the sample space of the experiment? Okay, so if it's flipped here, coin has 2 outcomes. It's flipped 3 times. 2 cubed is 8. There are 8 in the sample space. So since there are 8, I'm going to start with heads this time because that's my norm. I'm going to put 4 heads first. Okay, and then I'm going to follow that by 4. Oops, that doesn't look right at all. That did not look like a head. Make it about there. Okay, 4 heads, and then we'll make these like a little bit easier to make. T, T, T. Okay, now 4 heads, 4 tails. Okay, so because I'm going to always do half of them, whatever the first option is, and half of them, whatever the second option is. So then I'm going to do heads, heads, tails, tails, heads, heads, tails, tails. And then on the last row, I do heads and then a tails, and then heads and then a tails, and then heads and then a tails, and then heads and then a tails. Okay, so this is my sample space. This is the first of my sample space, head, head, head. This one is the last of my sample space, tail, 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 and all of those that are in between. 8 items in my sample space. Referring to the experiment in D, what is the probability of getting heads exactly twice? Okay, so D was right here. Okay, so what is the probability of getting heads exactly twice? Okay, so this one has 3 heads. This one has 2 heads. This one has 2 heads. This one has 1 head. This one has 2 heads. This one has 1 head. This one has 1 head. And this one has 0 heads. Okay, so I'm going to get 2 heads. What is the probability of getting heads exactly twice? Okay, so this one, this one, this one. I have 3 8s is the probability because I have 8 in my sample space, and I have 3 of those 8 options would give me exactly 2 heads. Okay, and so then it says, what is the probability of not getting heads exactly twice? Now, we could go back and count them up, or we could say, oh, that's the complement. And we could just say 1 minus 3/8 is 5/8. So the probability of not getting heads at least twice is 5/8, okay? Because it would be everything that we didn't count the first time. 1, 2, 3, 4, 5 eights were not 2 heads exactly. Okay, so Quinn runs a sandwich shop. Since she added turkey melt to the menu, 36 out of 120 customers have ordered the new sandwich. What is the probability that the next customer will order a turkey melt? Okay, so her probability of the next customer ordering a turkey melt is based on what has happened in the past. So this is an experimental probability, and 36 out of 120, and we're going to turn that into a little bit easier number to read. So let's divide this by 6 on the top, and let's divide this by 6 on the bottom, and maybe divide this one by 2, and divide this one by 2. So she's got a 0.3 or a 30% probability that the next customer is going to order a turkey melt. Now it says, what if Quinn has 50 customers for lunch? About how many are likely to order a turkey melt? Now you can see how important this is for somebody who is studying how much of a certain item she should have in stock. So if she, based on experience, has 30% or 3/10 of her customers that want a turkey melt, then she's going to take 3/10 and she's going to multiply by 50 customers, and she's going to make sure that she has enough materials on hand. We could cancel, and 5 times 3 is 15, and she's going to have 15 customers wanting a turkey melt. She can pretty much bank on that, so she'd better have enough ingredients to make 15 turkey melts. Okay, so G, state whether the probabilities found in problem E and F are examples of theoretical probability or experimental probability. Okay, so we go back to E, and okay, so E was talking about what happened when a coin was flipped. Okay, now this is based on D, which is talking about what is the outcome possibility of 3 coins being flipped. This one, D and E, this is theoretical probability. Okay, so we could say E is theoretical. Okay, because it is based on the theory behind how many favorable outcomes and how many total outcomes we have. So E is theoretical. Now let's go look at F. Okay, F was talking about experimental probability because it was not based on some theory or formula. It was based on what she was observing in her restaurant. Okay, so F is experimental. There is no empirical rule on this. This is experimental because it is based on what actually happened in her shop. Okay, so now we're going to start the written practice. Okay, so here we are on your written practice, and we're going to do the first 6 of these so that you should have no problem with your homework. If postage for an envelope cost 39 cents for the first ounce and 24 cents for each additional ounce, then what is the postage for a 12-ounce envelope? Okay, so we have 39 cents for the first ounce and 24 cents for each additional ounce. What is the postage for 12 ounce? So 12 ounces is, remember, the first ounce has been paid for by the 39 cents. And then each additional ounce after that, so 24 cents times the 11 additional ounces. Okay, so 24 times 11 would be 24, and 24 added together is 462 plus the 39. Okay, so it's going to cost 4 plus 9 is 13, and 10, and $3.03 to mail that post. 12 ounce envelope would be $3.03. Okay, that's pretty pricey. All right. An author writes an average of 8 pages per day. At this rate, how long would it take to write a 384-page book? Okay, now if we were going to do this with, say, our rates, we would say 8 pages per day. Okay, and we would say we're writing now in each day, the author would write 8 pages. If I want to make it multiplication, I need pages on the bottom times 384 pages. Okay, so now pages is going to cancel pages because I set it up right. And to find the number of days, I will divide 384 by 8 because 8's on the bottom. And you knew that's what we were going to do, didn't you? Okay, so 8 into 3. So 8 goes into 32 4 times. 4 times 8 is 32. Subtract and get 6, and then pull down your 4. 8 into 64 is 8. That's going to take 48 days. 48 days of writing. Pete saw that he was 200 yards from shore when he dove out of the boat. It took him 49 seconds to swim the first 50 yards. At that rate, how much longer will it take him to reach the shore? Okay, well now if you are saying at that rate, you are discounting the fact that Pete could get tired. Okay, so he's doing 49 seconds per 50 yards. So we're going to assume that he's going to keep on that very fast pace. Okay, and he's going to swim 200 yards. Okay, so 200 divided by 50 is 4 and 1. So 49 times 4 is 36. Carry the 3, 16, 19, and 196 seconds. Okay, well, that's kind of awkward. 196 seconds. So 196 seconds is how many minutes? Okay. Oops, it says how much longer. How much longer? So we would say it's not 196 seconds. It is how much longer would only be 3, right? Because he already swam the 49. He has to swim 3 times that more. So it's not 196 because it didn't say how long will it take him to swim the 200 yards. It said how much longer will it take him to reach the shore. So 49 times 3 is how much longer, which we have to multiply again, is 27, 12, 13, 14. And then how many minutes is that? Okay, so 147 times divided by 60. That's going to go 2 minutes. 2 times, that's 120. Okay, and then that's going to have 27 left. So 2 minutes and 27 seconds left over. 2 minutes and 27 seconds. Number 4, Alonzo chose a name from a box, read the name, then replaced it and mixed the names. He repeated this experiment several times. Out of the 20 names he chose, 12 were 8th graders. What is the experimental probability of choosing the name of an 8th grader based on Alonzo's experiments? Okay, so he chooses a name from the box, he read the name, and then he replaced it back in the box and mixed the names up again. He repeated this experiment several times. There were 20 names, okay, and 12 were 8th graders. Okay, so does he have an equal chance every time of choosing the names? And he does. Okay, so because he chose 12 that were 8th graders, we can assume that there were probably about 12 out of 20 of them were 8th graders. This is what is the experimental probability of choosing the name of an 8th grader. So 12 over 20 is the experimental probability, which we would say is 6/10 when we simplify it, which we could say is 60%. Okay, if half of the names in the box are 8th graders, what is the theoretical probability of choosing the name of an 8th grader? So now they're actually telling us what is in the box. And out of the 20 names, there are 10 8th graders in the box. So the theoretical probability, so this one was the experimental probability based on what actually happened. But theoretical, there are 10 out of 20, which we know is 50%. That is the theoretical probability. So theoretical was 50 and experimental was 60%. What is the experimental probability of choosing the name of an 8th grader? Okay, so that one was 60% was experimental. So that was 60%. And that was 50%. All right, the next one. There are 18 marbles in Molly's bag. 2 of the marbles are yellow. If Molly chooses one marble at random, find the theoretical probability that she will choose a yellow marble. What is the probability she will not choose a yellow marble? Okay, so there's 18 marbles in the bag, and there are 2 favorable ones. There are 2 that are yellow. So 1 out of 9 is the simplified fraction. So she has a 1/9 probability of, that's her theoretical, based on what's actually in the bag. Okay, so it says, what is the probability she will choose a yellow marble? It's 1 out of 9. So what is the probability she will not choose a yellow marble? Wouldn't it be 1 minus that, which would be 8 out of 9? So this is the probability of not yellow. Okay, and then 1 over 9 is the probability that she draws a yellow. Number 6, use the figure at the right to answer A and B. What is the area of this triangle? Okay, so an area, remember, area of a triangle is 1/2 base times height. Okay, what is the perimeter of the triangle? It's adding up all the sides. Okay, now, how did I figure this one out? This one's 10. This one's 6. Now, remember our right triangle, the most famous right triangle is 3, 4, 5. Since 10 divided by 2 is 5, and 6 divided by 2 is 3, we can be pretty sure that this one right here is 8 because 8 divided by 2 is 4. Remember, this one, the hypotenuse, is always the longest side. So this one is in the pattern of 3, 4, 5, so it's 6, 8, 10. All right, so once I figure that out, that this is one of those famous, what we call Pythagorean triples, then we're going to say 6, 8, 10. When I add them all together, that's 14 plus 10 is 24. So the perimeter is 24. Okay, 24 meters. And the area is 1/2. Base, we'll call that 6. Height, we'll call that 8. 6 times 8 is 48. Divided by 2 is 24. Now, there's not very many triangles that have the area and the perimeter the same. But remember, area is meters squared, or square meters. And that is the end of lesson 32. And I think I've learned how to use this cool new tool. So see you later, guys. This is Mrs. A, and may God bless your day. Have a great weekend.